Once we've segmented out words or tokenized them, we need to normalize them and stem them. So normalizing means different things. For information retrieval, for example, we require that the index text and the query terms have to have the same form. So we want to match u.s.a. to USA if somebody asks a question or a query with one of them and the answer has the other, we want them to match. So it's like implicitly defining some kind of equivalence class of terms. We might do this by always deleting periods, for example. We might have a rule that takes u.s.a. to USA. An alternative is some kind of asymmetric expansion. So for example, let's say we're doing information retrieval. If I enter the term window, I might want to search for window or windows or any morphological variant of the word window. But if I enter capital W windows, I might only want to search for capital W windows because the person's presumably looking for the product and not the part of your house. And this is a potentially more powerful algorithm, but less efficient and much more complicated. So in general, we use symmetric and relatively simple expansions. So for example, in information retrieval, we generally reduce all letters to lowercase, since users tend to use lowercase, and with some small exceptions. So for example, if we see uppercase in the middle of a sentence, like General Motors, we might want to keep the case. And this matters for distinguishing the verb fed from the Federal Reserve Bank with a capital F, or a group like SAIL, the Stanford Artificial Intelligence Lab, from the verb sail. And it turns out that for sentiment analysis or machine translation or information extraction, case is in fact very helpful. So there's a big difference between US and us. We also often want to do lemmatization, so we're reducing our inflections or variant forms to their base form. So words like am and are and is will get lemmatized into be, car, cars, car apostrophe s, and so on, get lemmatized to car. So a phrase like the boy's cars are different colors should get lemmatized to the boy car be different color. So in general, the task of lemmatization is finding the correct dictionary headword form for a word form that you're given. And of course, this is very important for all sorts of applications, particularly machine translations, where, for example, if you have a Spanish verb like quiero, I want, or quieres, you want, it's very important to know that this is the same lemma as querer, the verb to want. So this general topic of looking at parts of words leads us to morphology. Morphology is the study of morphemes, and a morpheme is the smallest unit that makes up a word. And we usually distinguish two kinds of morphemes. Stems, that's the core meaning-bearing units in a word. And affixes the bits and pieces that adhere to the stem. Often they have grammatical functions. So on this particular slide, in fact, stem is a stem and S is an affix. The word affix, just to confuse us, is a stem, and there ES is the affix. So there's an affix. There's an S, and there's an S, and meaning full, there's another affix, and so on. So stemming is the task of taking off these affixes to reduce terms to their stem. And it's particularly historically derived from information retrieval, although it's used in all sorts of applications. We use the word stemming when we specifically mean a kind of a crude chopping off of affixes. And this is, of course, a language-dependent kind of process. So the English word automate, automates, automatic, automaton, we'd like them all to refer to the same stem, automat. So stemming is like a simplified version of lemmatization, where we pick a prefix of the word, use that to represent the word, and we chop off all the suffixes that are relevant, leading to that stem. So here's an example little text. For example, compressed and compression are both accepted as equivalent to compress. That's the text. And if we stemmed that text, here's the resulting output. So you can see that that we've lost the E on example, and compressed and compressing have both turned into compress, and here we used R. We could have used B as our representation of R, but this particular example we used R, and so on. The simplest algorithm, the most commonly used one for simple stemming of English is the Porter algorithm. And the Porter's algorithm is an iterated series of simple rules, replace rules. So, for example, one set of rules, rule step 1A, takes strings like SSES and replaces them with SS. So in a word like caresses, it chops off the ES of caresses. Or a rule that takes IES to I, chops off the IES of ponies and leaves pony. We're going to use pony with an I as a representation in Porter stemming of pony. And the rules operate in order so that at this point, if there's any SS's left, they stay as an S, but any other S's get deleted at this point. So the S of cats is deleted while the SS of caress is kept. Similarly, in step 1B, we remove all of the ings and the eds. So we want to cross off the ing of walk and the ed of plastered. But we specify the rule very carefully that in the Porter stemmer, only words with a vowel get their ings removed. And that's because a word like sing, only words where there's an additional vowel before the ing. So a word like sing, which has no extra vowel, sing only has one vowel, the vowel in ing, stays as sing. But walking, which has a vowel and in addition a vowel before the ing, is allowed to delete the suffix. So if a word has a vowel followed by ing, the ing is deleted. And there's lots of other such rules. So ational turns into ate, so we can cross off the all of relational, and the shun and end up with relate, and eyes-er to eyes, and so we cross off the R, and so on. And the rules get even more complicated. So as you get to very long stems, you're going to remove the all of revival and the ubble and so on. Let's look again at this rule that strips ing and practice using the Unix tools that we saw in the last section to look at morphology in a corpus. So remember, why are we stripping the ings only if there's a vowel preceding the ing? Here was the rule. And remember we said that in a word like walking, we have a vowel before the ing, and so it's okay to remove the ing. In a word like sing, there is no vowel before, there's no letters at all before that S, there's no previous vowels, and so sing, the rule doesn't apply. And let's do a little search for words ending in ing in Shakespeare. So we're going to first take all of Shakespeare and turn all the non-alphabetic characters turn all the non-alphabetical characters into new lines. So we're going to get one word per line. Then we're going to translate all of the uppercase to lowercase. So we're combining all the uppercase and lowercase words. And now let's grep out. Grep is a program for finding any line that contains a regular expression in a file. Very useful Unix program. So we're going to look for the regular expression ing $. And so we'll find all words ending in ing, and let's sort them, and then we'll just take one copy of each and count them, and then sort them by the counts. Let's see what words we find ending in ing in Shakespeare. And what we see is lots of these words are not words that in fact we would like to remove the ing from. So we have words like king and nothing and thing and ring and something and sing and anything and spring. So there's a lot of words, a lot of very frequent words in fact, that it would be a bad idea to remove the ing. If we remove the ing from king, we'd get k, and so on. Remove the ing from spring, we'd get spr. So let's modify our rule that we did. Instead of saying grepping for all words ending in ing, let's just go back and change that to grep for all words with a vowel. We'll just make it be A, E, I, O, U. Simulate our vowels with just the vowel letters. And we need some way to say there's a vowel, and then anything can happen in between, followed by the ing. Well, how do we say anything? dot means any character, star meaning 0 or more of those. And now let's look at what words we get back from that pattern. And now, since we've specified that the word has to start with a vowel, we've done a much better job of finding 2-syllable words where the ing, in fact, is supposed to be stripped off. So there are still some problematic words like nothing and something. We don't want to get noth and someth and anything. But otherwise, and maybe not cunning, but otherwise, we've done a pretty good job of making the rule a little bit better. So there's a little explanation of how the Porter stemmer works, and then how we can actually use our Unix tools to do a little corpus linguistics to help write rules of this kind. So that's a simple example of morphology. It turns out that in some languages, much more complex morphology is necessary, and Turkish is the famous example of this. So here's a word in Turkish which I won't be able to pronounce for you, which means behaving as if you were among those whom we could not civilize. So I assume it's the kind of thing your mother says to you when you've been particularly naughty. And in Turkish, this is one word. So it's a very long word with a lot of stems. We have the civilized stem, and an affix meaning to become, and an affix meaning cause, and an affix meaning not able, and so on. So in languages like Turkish, and as we saw earlier for the very long nouns in German, we're going to have to do a richer and more complex morpheme segmentation. So as we've seen word tokenization, and now we've seen that words will have to be normalized and stems to map them to a normal form.